So let's look at some additional practice problems for Chapter 2. First, what is an isotope? Well, how do you describe an isotope? I'm very intentional with the language in this course because, well, you need to understand what you're talking about. You need to be able to communicate as a scientist. And so you need to understand the terminology. So when I say things like, it's an isotope, you should be able to immediately think in your brain what an isotope means and be able to picture it, see it, understand it, and communicate that language. An isotope is something that's the same element but has a different number of neutrons in its nucleus, which causes the atom to have a different mass than another atom of the same element. So same element, but different number of neutrons in the nucleus, causing the atom to have a different mass than another atom of the same element. So how can something that's the same have a different number of neutrons? How is it the same then? Remember, an element is defined by the number of protons it has. Every atom has protons, neutrons, and electrons. If we change the number of electrons something has, then we change something from a neutral species to a charged species. If we lose electrons, we're forming a cation. If we gain electrons, we're forming an anion. But it's still the same element. The protons is the number of positively charged particles in our nucleus, and that's what defines what the element is. The only time we can change the number of protons in the nucleus is when we get into nuclear chemistry. You'll see that near the end of second semester, but in first semester, you're not responsible for that. In first semester, we will not be changing the number of protons in our nucleus. The other thing we have in our atom, though, is neutrons. Neutrons also reside in your nucleus, hence why the nucleus is very mass dense. Most of the mass of an atom is contained in the nucleus. The electrons weigh very little, roughly 1/2000th the mass of a proton. A neutron is roughly the mass of a proton plus an electron. And protons and neutrons are roughly the same mass. We say they're approximately 1 AMU each. So if we change the number of neutrons in our nucleus, we haven't changed the identity of our element at all, but we have changed the mass of the compound because every addition of a neutron is going to add 1 AMU to our system. So an atom represented by 106 SN has how many neutrons, protons, and electrons? If you get a question like this, the first thing you want to do is you want to look and see what element is SN. SN is one that's not intuitive because its elemental symbol is based on its original naming system, not its more common name that we call it now. But SN actually represents tin. Go to your periodic table and find the atomic number of tin. You'll find that tin has an atomic number of 50. That means that the number of protons is equal to 50. Because there is no charge listed here, it just shows it as a neutral atom, we know that the number of electrons must also be 50. Because in order for it to be neutral, it has to have the same number of protons as electrons. Lastly, we want to know the number of neutrons. Remember, we get that from this mass number. This number here, this 106, is equal to the number of protons plus the number of neutrons we have, assuming that each one contributes 1 AMU. So in that case, the number of neutrons we have will be 56, because of course 56 plus 50 gives me 106. An atom represented by 18O2 minus has how many neutrons, protons, and electrons? Well, you should know this one. Oxygen is O. And look up the atomic mass, or atomic number, I mean. The atomic number of oxygen is 8. Therefore, I know my number of protons has to equal 8. When I look at number of electrons, though, I notice I have a charge here, which means I need to factor that into the number of electrons I have. I see it's a -2 charge, which means I have 2 more electrons than protons in my atom, which means I have 10 electrons. And my neutrons, I'm going to find the same way as I did in the previous example. 18 is equal to my number of protons plus my number of neutrons. Therefore, I have 10 neutrons in this atom. Lastly, an atom represented by 53 Fe3+ has how many neutrons, protons, and electrons? You should know this one. It's one of the ones that you guys need to know, but Fe is iron. Again, it's Fe because it's based on its original naming, ferric and ferrous. But you do have to recognize that iron and Fe are the same element. Look up the atomic number. And we find the atomic number here to be 26. That means I know that this has 26 protons. For number of electrons, I notice now I have a 3+ charge. In order to get a positive charge, that means I have less electrons than protons. Therefore, since it's +3, I must have 23 electrons and 26 protons to cause that +3 charge. Lastly, my number of neutrons. I've got a mass number here of 53, which means 53 minus 26 equals my number of neutrons, and that gives me an answer of 27. Some more questions for you to think about. I want you to pause this video and think about what these questions are asking you. What is an ion? What is a cation? What is an anion? We use these terms very intentionally because, again, it's the language of chemistry. And when you hear the word ion, I need you to think charged particle. I need you to immediately realize or think about the fact that the number of protons is not equal to the number of electrons. Just calling something an ion does not tell me if it's positively or negatively charged, but it does tell me that I do not have an equal number of protons and electrons. What is a cation? When you hear cation, I need you to think positively charged ion. So you've got the ion there. You need to remember that cat means positive. If it's positively charged, that means my number of protons is greater than my number of electrons. And what is an anion? We've got ion here telling me it's a charged particle, but an means negative. It is a negatively charged particle. To be negatively charged, the number of protons must be less than the number of electrons. So ion just means they're not equal to each other. Cation means that I have more protons than electrons, and I therefore have a positively charged species. And anion means I have more electrons than protons, and therefore have a negatively charged species. Okay, let's look at some examples, some other types of examples other than just definitions. There are two stable isotopes of copper, copper-63 and copper-65. Remember, we can write them like this. I could also say Cu63 or copper-63. All mean the exact same thing. Using the atomic mass of copper, determine which isotope is more abundant. Well, go to your periodic table and look up where copper is. According to my periodic table, the atomic mass of copper is 63.546 AMU. If I know these are the two stable isotopes of copper, that means those are the two isotopes that contribute the most to this mass of copper. How do I determine which one's more abundant? Well, where does my atomic mass lie? My atomic mass lies closer to 63. So I'm trying to figure out between these two, where does this lie? It's lying closer to 63. Shorter distance, longer distance. So that means that copper 63 is more abundant. So there's often math problems in this class. Yes, this is general chemistry. It's math heavy. But sometimes doing math isn't appropriate. Sometimes you just need to understand the concept, and it's actually a pretty quick answer. Okay, let's look at doing this with math. An element has 3 naturally occurring isotopes with the following masses and fractional abundances. I have 27.97 AMU with a 0.922 fractional abundance. I have 28.974 AMU with a 0.0469 fractional abundance, and I have 29.297 AMU with a 0.0310 fractional abundance. Now, you may be able to guesstimate what element you're looking at here, since that's what's the identity of the element. You may be able to guesstimate the element based on where you see the mass lying here. You'll probably get pretty close. Some of these elements are really close together, so be careful doing that. But if you're asked a question like this on an exam or a quiz, we expect to see your work. Even in a multiple choice question, we need to see work for your credit. So still show us the work, even if you think, oh, I can go ahead and guess that based on where the abundances lie. So how do you do this? Well, to figure out your atomic mass, you're going to take the AMU, or the mass of the isotope itself, and multiply it by its fractional abundance. If these had been presented in percent form, so if this said 92.2%, you would have to put it back into fractional form. So make sure you're comfortable transferring between percent and fractions. So we've got 27.977 AMU times 0.922 plus 28.974 AMU times 0.0469 plus 29.297 AMU times 0.0310. When I calculate all of this out, I'm going to get an atomic mass of 28.1 AMU. When I look at the periodic table, I see this matches closest to silicon. Silicon has a mass of around 28. Depending on what table you look at, 28.086, 28.09. If rounded to 3 sig figs, which we need to do because I have 3 sig figs in each of these measurements here, then it will be a mass of 28.1. So, can you identify things off the periodic table? Can you identify where your metals are, your nonmetals, your metalloids, your alkali metals, alkaline earth metals, transition metals, halogens, noble gases? You need to find these very quickly because there's a lot of properties that are associated with these elements or compounds themselves, so you need to be able to recognize very quickly where these reside. So, how do you distinguish between your metals and your nonmetals? Well, that's when you need to know where your metalloids are, your stair step, as I call it. If you look at the stair step, your metalloids fall on this step. Got boron, silicon, germanium, arsenic, antimony, tellurium, polonium, and acetane. These are metalloids. Oops. So the stair step is your metalloids. Why do I care? Because your stair step separates your metals from your nonmetals. Anything this direction from your metalloids is a nonmetal. Anything this direction is a metal. So the bulk of that table is metals. But you need to be able to recognize where that stair step is. Those, again, are your metalloids, and anything to the right of that is your nonmetals. Anything to the left of that is your metals. Let's see, what is next? Your alkali metals. Alkali metal are what we call group 1. So not hydrogen. Hydrogen fits here because of electron configuration, which we'll talk about a little bit later in the semester. But lithium, sodium, potassium, rubidium, cesium, and francium, these are your alkali metals. Group 2, alkaline earth metals. Your transition metals is this block in the middle. We call this your D block. You'll learn more about that later in the semester. But this is your D block. And these encompass your transition metals. So just that block. Halogens is group 17. It starts with fluorine. And lastly, your noble gases is group 18. And again, why do we care? Because they follow specific types of reactions. They undergo specific chemistry based on where they fall in that table. The table itself, again, has been constructed to put similar properties together. And so you need to understand where all of these reside so that you can better understand and predict what's going to happen. Okay, another thing we covered in this chapter is molar mass. So let's look at this. What is the molar mass of zinc chloride? Well, first thing I have to do, or ZnCl2. You're going to learn naming in chapter 3. ZnCl2 is zinc chloride. So you need to be able to recognize, looking at this means I have 1 zinc and 2 chloride atoms per every compound. This is a formula unit. It is an ionic compound. We're going to learn more about ionic in the start of chapter 3. But if you have a metal and a non-metal, it makes an ionic compound. So it doesn't truly form a molecule. It forms what we call a formula unit. We'll cover more of that again as we start chapter 3. But each formula unit of zinc chloride contains 1 zinc and 2 chlorides. So I've got 1 zinc, 1 times 65.39 grams per mole. Again, I'm getting that 65.39 grams per mole directly from my periodic table. This equals 65.39 grams per mole for the zinc. I have 2 chloride ions. If you look up chlorine, 35.45 grams per mole. You may have heard me referring to this as chloride. It is chloride. We'll talk about that more as we get into chapter 3. But it's chloride just means it's an ion. And again, that just means it has a different number of electrons, which means it hasn't changed the mass of the species. If I add this up, this is 70.90 grams per mole. Again, why am I doing these individually in steps? It's because I need to figure out where my sig figs are. So I see here I had 4 sig figs, 4 sig figs, 4 sig figs, 4 sig figs. When I add this up, I get a molar mass of 136.29 grams per mole. I finish with 5 sig figs. That's because in this step here, I'm doing addition. And so over here, I was following multiplication rules. Now I need to follow addition rules. But the molar mass of the species 136.29 grams per mole. What is the molar mass of magnesium phosphate? Mg3PO42. This 3 down here means I have 3 magnesiums, which means 3 times 24.31 grams per mole. Again, that's 24.31 straight from the periodic table. It's the atomic mass of magnesium. This gives me 72.93 grams per mole. I then have PO4, but I have a 2 outside of here. This 2 is distributed through the entire polyatomic. That's why there's a parenthesis there. So that means I have 2 phosphorus, 2 times 30.97 grams per mole, giving me 61.94 grams per mole, and 8 oxygen. 8, because I have a 4 down here, so 2 times 4 equals 8. 8 times 16 grams per mole, giving me 128.0 grams per mole. Again, 4 sig figs in each answer. Add these all up, and when you add them up, you're going to find a total mass of 262.9 grams per mole. I'm going to stop at the first decimal place here because now I'm following addition rules, and so I need to stop at the first decimal place because it's limited by oxygen. 262.9 grams per mole is our molar mass of this species. What about the molar mass of water? It's also known as dihydrogen monoxide, so that's what's written in your notes, dihydrogen monoxide. Again, we're going to learn naming in the very next chapter, but it's always good to expose you to it now. Looking at this, I've got 2 hydrogens, 2 times 1.008 grams per mole, 1 oxygen, 1 times 16 grams per mole. This gives me 2.016 grams per mole. This gives me 16 grams per mole. Adding them all together, you're going to get a molar mass of 18.02 grams per mole. So dihydrogen monoxide, or water, has a molar mass of 18.02 grams per mole. If you have 18 grams of water, you've got 6.022 times 10 to the 23rd water molecules. That's what this is telling me. How many moles are present in 9.25 times 10 to the 24th molecules of C3H8? So I'm trying to find number of moles, and I'm given number of molecules of C3H8. In this case, I don't really care what the identity is because I don't need the grams of it at all. I'm just converting from molecules to moles, which is just using Avogadro's number. I'm still going to label it as C3H8 because the question tells me it's that species, but it doesn't matter for the math. So I want to know the number of moles, C3H8, and I'm starting with 9.25 times 10 to the 24th molecules of C3H8. In order to go from molecules to moles, I'm going to use Avogadro's number. I know that 1 mole of C3H8 contains 6.022 times 10 to the 23rd molecules of C3H8. When I do the calculation here, in my calculator, I'm going to put 9.25 times 10 to the 24th, divide that by 6.022 times 10 to the 23rd. Make sure when you're doing this times 10 to the 24th, 23rd, etc., you're using the button that looks like this on your calculator. That will get you to the right answer. This gives me 15.4 moles of C3H8. How many moles of aluminum does 3.7 times 10 to the 24th aluminum atoms represent? So I want moles, and I'm given number of atoms. Even though it's number of atoms this time instead of number of molecules, it's set up the exact same way because Avogadro's number is just a number. It's a unit for numbers. 1 mole of anything contains 6.022 times 10 to the 23rd of that thing. So number of moles of aluminum equals 3.7 times 10 to the 24th aluminum atoms times 1 mole of aluminum divided by 6.022 times 10 to the 23rd aluminum atoms. And this gives me 6.14 moles of aluminum. Calculate the number of atoms in each sample. When I'm saying atoms, I want to know number of atoms of that actual thing, meaning I'm looking through Avogadro's number. I'm giving this in grams, which means I'm going to have to convert from grams to moles, and then moles to number of atoms. So I want number of atoms of chromium. I'm starting with 14.995 grams of chromium. When I look at the periodic table, depending on which table you look at, some tables only represent the mass of that species to 2 decimal places. In this case, I want to represent the atomic mass to 3 decimal places for chromium, because chromium's about 52 AMU. I want to represent it to 3, though, because I don't want that mass measurement to limit my significant figures here. I want my measurement to control how many sig figs I have, and I have 5 sig figs here. So I'm going to look at a slightly more accurate periodic table to get the measurement of the mass to 1 more decimal place. So times 1 mole of chromium to 51.996 grams of chromium. Now at this point, this would cancel out my grams and leave me with moles. Now that I'm in moles, I can easily convert to number of atoms with Avogadro's number. 6.022 times 10 to the 23rd chromium atoms divided by 1 mole of chromium gives me 1.7320 times 10 to the 23rd chromium atoms. The other thing to note here is this 0 I have to put here. Your calculator is going to give you 1.732. That's not the correct answer. I need 5 sig figs, so I need to add a 0 there to have 1 more sig fig. Okay, how about number of platinum atoms? If I have 12.899 grams of platinum, how many platinum atoms does that contain? When I look at the periodic table, 1 mole of platinum equals 195.08 grams of platinum. Platinum is one of our heavier metals. It's also quite expensive. Now that I'm in moles, so again, this cancels my grams. I forgot to specify earlier, this cancels my moles, gives me atoms. Now I've canceled my grams. Now I can go ahead and use Avogadro's number, 6.022 times 10 to the 23rd. Platinum atoms per 1 mole of platinum. That cancels my moles of platinum and gives me platinum atoms. And my answer here, 3.9818 times 10 to the 22nd platinum atoms. And lastly, what about sulfur? I'm starting out with 39.733 grams of sulfur. 1 mole of sulfur, when I look at the table, tells me 32.07. That's the most accurate it's going to be. I need to put a 0 here to keep my sig figs. 32.070 is the actual next measurement for sulfur. At this step, that cancels my grams of sulfur. And I'm in moles. Now I can use Avogadro's number, 6.022 times 10 to the 23rd sulfur atoms divided by 1 mole of sulfur. And I find this to be 7.4609 times 10 to the 23rd sulfur atoms. Now again, these numbers are really big. It's hard to justify if these numbers make sense or not, and I understand that. But what I do want you to do is I do want you to kind of try to think about this. If you start with 14.995 grams, that is less than the mass needed for 1 mole. This number is smaller than Avogadro's number. So yes, your number makes sense. That's the best analogy I can make for it. I don't understand the numbers that big. It doesn't make sense in my brain for a number to be that big. I just understand it's really big. But that's how I kind of check myself. I'm like, okay, it is smaller than Avogadro. I'm probably on the right track. Same thing here. 12.899 is a lot less than 195. And I see that this number is actually kind of a lot less, or even to the times 10 to the 22 instead of 23. So that number makes sense to me. And last one, 39.7 is bigger than 32. I expect this number to be bigger than Avogadro's number, and it is in fact bigger. So when I tell you guys to check your answers, on some questions I understand it's very difficult to think about how do I check this answer, but that's what I mean. Okay. How many phosphorus atoms are in 4.29 grams of aluminum phosphate? I want to know my number of phosphorus atoms. I'm starting with 4.29 grams of aluminum phosphate. First thing I'm going to do is I'm going to convert to moles of aluminum phosphate. Remember, when in doubt, convert to moles. To do that, I need the molar mass of aluminum phosphate. So I'm not going to add them up individually here, but in order to do this, you need to recognize you have 3 aluminum, 2 phosphate, and 8 oxygen. 270.9 grams of aluminum phosphate. Now that I'm in moles of aluminum phosphate, I'm going to go ahead and convert to moles of phosphorus specifically. I know I have 2 phosphorus for every 1 mole of aluminum phosphate. Now that I've got moles of phosphorus, I apologize. Now that I've got moles of phosphorus, I can use Avogadro's number to find the number of phosphorus atoms. 6.022 times 10 to the 23rd phosphorus atoms to 1 mole of phosphate. Phosphorus. I keep saying phosphate. I apologize. It is phosphorus. Phosphate is PO4 3-. When I calculate this out, I get 1.91 times 10 to the 22nd phosphorus atoms. Does that answer make sense to me? Yeah, this number is actually pretty small, especially compared to this. How many hydrogen atoms are in 1.32 moles of magnesium acetate? You may ask why the formula is written like this. You're going to see it written a few different ways. This is the way I'm going to write it in this class. This is the way I see acetate. It's an organic compound. You'll learn more about the structures later on in the semester. You'll also see this written as C2H3O2, which is completely fine. Oops. Sorry, C2H3O2. Completely fine. I just don't write it that way. You need to be able to recognize this. You can write it this way. I recognize it. I have to think about it for a second, but I do realize what it is when I think about it, but I will always writing acetate this way instead. So 1.32 moles of magnesium acetate. I'm already in moles of magnesium acetate at this point, so I don't have to even deal with the molar mass. I can just use my conversions here. I see that for acetate has 3 hydrogens in it, but I have a 2 out here. So I have 2 acetate ions for every 1 magnesium acetate compound. So I have to apply that 2 to this. What does that mean? That means I have 6 moles of hydrogen atoms for every 1 mole of magnesium acetate. This gets rid of my moles of magnesium acetate and gives me moles of hydrogen atoms. Now that I've got moles of hydrogen, I'm going to multiply by Avogadro's number, 6.022 times 10 to the 23rd hydrogen atoms to 1 mole of hydrogen. And the final answer here, 4.77 times 10 to the 24th hydrogen atoms. I hope this isn't too messy for you guys to read. I'm sorry. I'm not very good at writing on little screens. Okay, what species is represented by the following information? What if you got a question like this one? First thing you should do, if you get a question like this, immediately look at the protons. The protons are going to tell you the element you have. Number of protons equals 47, which is your atomic number. And when I look at the periodic table and find 47, it equals silver. I see that I have 1 less electron than proton. Which means I have a cation, and it means this has a +1 charge. The last thing I need to do is determine which isotope I have. To get your mass number, it's the number of protons plus the number of neutrons. So 47 plus 62 equals 109. So I represent this as 109 Ag+. It's telling me it's an isotope 109 of silver, and it's a silver ion. Cation specifically, but we call it the silver ion. We'll, again, learn more about naming in the very next chapter. How many chloride ions are in 25 grams of aluminum chloride? AlCl3 is aluminum chloride. I want number of chloride ions. Starting with 25 grams of aluminum chloride. Always, always, always convert to moles. In order to do that, you do need the molar mass of aluminum chloride. So you should look at your periodic table. You have 1 aluminum and 3 chloride ions. So look up the mass for aluminum and chlorine. You're going to look up the mass for chlorine, but chloride ion is going to weigh the same. You're going to find the mass here to be 133.3 grams per mole. So 133.3 grams of aluminum chloride per 1 mole of aluminum chloride. Now that I'm in moles of aluminum chloride, I can convert over to moles of chloride ions. 3 moles of Cl- ions. How do I know it's Cl-? I will teach you guys that in the very next chapter. Halogens always want to be a -1 charge. We talked about that, but we're going to get more exposure to that in chapter 3. For every 1 mole of aluminum chloride. And now that I have moles of chloride ions, I can use Avogadro's number to actually determine how many chloride ions do I have. 6.022 times 10 to the 23rd chloride ions to every 1 mole of chloride ions. And when I calculate this out, I get an answer of 3.39 times 10 to the 23rd Cl- ions. Again, asking myself, does the answer make sense? Well, 25 is less than 133. This is less than 6.022. So that's the best correlation I can give. How many oxygen atoms are there in 4 grams of sodium dichromate Na2Cr2O7? So now I want to know the number of oxygen atoms. If I'm starting with 4 grams of sodium dichromate. One mole of sodium dichromate weighs 262.0 grams per mole. I know, based on this formula, I have 7 oxygens for every 1 compound. Now that I'm in moles of oxygen, again, you can always check by crossing out what you've canceled out. I've got moles of oxygen now. Now I can use Avogadro's number and determine my number of oxygen atoms. And I find I have 6.44 times 10 to the 22nd oxygen atoms. I have started with 4 grams. The molar mass of sodium dichromate is pretty large. So to me, yes, the answer does make sense. A certain gas canister contains 4.82 times 10 to the 18th gas molecules. How many moles of molecules are present? Note, I don't care what it is. I'm just going from number of molecules to number of moles of molecules. It makes no difference to me what the identity of the species is here, because I'm only going to use Avogadro's number. I'm only determining number of moles, which is a direct number correlation. So number of molecules is equal to 4.82 times 10 to the 18th molecules times 1 mole of molecules per 6.022 times 10 to the 23rd molecules. That cancels those out, and I'm given moles of molecules here. And when I calculate this out, I get an answer of 8.00 times 10 to the minus 6th moles of molecules. Does that answer make sense? It's pretty small. This is a lot smaller than Avogadro's number, so yeah, the answer does make sense. How many molecules of glucose, C6H12O6, are present in 25 grams of glucose? So, number of molecules, meaning Avogadro's number, starting with 25 grams of glucose, which is C6H12O6. You do have to find the molar mass here. When you add this up, you should find the molar mass to be 180.2 grams per mole. So, number of molecules, starting with 25 grams, convert to moles, now that I'm in moles of glucose, I can convert to number of molecules of glucose. 6.022 times 10 to the 23rd, C6H12O6 molecules, divided by 1 mole of C6H12O6 molecules. Gives me 8.36 times 10 to the 22nd, C6H12O6 molecules. 25, a lot smaller than 180, So an answer of 8.36 times 10 to the 22nd makes sense. What is the mass in grams of 3.77 times 10 to the 10th water molecules? Molar mass of water, 18.02 grams per mole. So I want to know the number of grams of water. I'm starting with 3.77 times 10 to the 10th water molecules. First, I need to convert to moles. 1 mole of water contains 6.022 times 10 to the 23rd water molecules. Now that in moles of water, that cancels out my molecules, I can convert to grams of water. Using my molar mass, 18.02 grams of water to every 1 mole of water. Gives me 1.13 times 10 to the negative 12th grams of water. That answer seems really, really small. Does that make sense? Yeah, it really does, because this answer is really small. This is less than half of a mole of water, and 1 mole of water only equals 18 grams. Okay. What is the identity of the element represented by the graph? When you get a graph like this, again, this is from what we call a mass spec, or a mass spectrophotometer. It's looking at the mass of something we have, and it's separating out the individual isotopes of an element. And then it normalizes them, so it takes the number of particles you got at the highest weight, and it equals that to 100%, and it gives the others a relative percentage from that. So we see that we have an isotope 208 at about 100%. Isotopes 206 and 207 are probably about 50% each. And then we have a small contribution here at 204. The way I would do this is I would think, okay, 208 is contributing about half the mass to that. 206, 207 contributing the next part to it. So I'm going to guess the mass is probably a little either around about 207 AMU or slightly higher. And so I'm going to look at the periodic table, find the element that's closest to 207, and I see lead at 207.2 AMU. Completely matches up with the data we're provided here. The other options near there on the table would be thallium has an atomic mass of 204.4. And bismuth is 209. Those are not anywhere near the data I'm seeing presented here. Sorry, that should be a T and an L. That's not anywhere near the data presented here, so this is in fact lead. What if I'm given information like this? What's the identity of the element with the following mass and percent abundances? Well, remember when you're given percent abundances, you do need to put these into fractional form, which means that this really equals 0.0019, 0.0025, 0.8843, 0.1113. If you're unsure on how to go to fractional, take that number and divide it by 100. Now let's go ahead and figure out the AMU for this species. I have a mass at 135.90714 with a percent abundance of 0.0019. I have a mass at 137.90599 with a percent abundance of 0.25, which is 0.0025 for fractional. I have an isotope at 139.90543, Percent abundance is 88.43, so fractional abundance is 0.8843. My last isotope comes in at 141.90924, and its fractional abundance is 0.1113. When I calculate all of this up, before I round for sig figs, I get about 140.1 grams per mole. When I round for sig figs, I need to have no more than 2 sig figs because of my fractional abundances here. So I would say 140 grams per mole. Looking at the periodic table, I'm going to say that this is going to be the element of cerium. Cerium is atomic number 58. It's at the bottom of the table. It's what we call your F block. It's the block we pull out of the table. But if I look at cerium, its atomic mass here is 140.1 grams per mole. So used to writing grams per mole. I forgot to write AMU here. I apologize. It means the same difference, depending what calculations you're doing. But cerium is 140.1. Before that comes lanthanum at 138.9. It's a little too low. And above it comes praseodymium at 140.9. Little high for the value we're actually looking for when we're rounding this to about 140. So we're going to go ahead and say this is cerium. That's how it's fully spelled. This is its elemental symbol. Another isotope example. Naturally occurring boron has an atomic mass of 10.811 AMU. It's composed of 2 isotopes, boron 10 and boron 11. Atoms of boron 10 have a mass of 10.0129 AMU, and those of boron 11 have a mass of 11.0093 AMU. Calculate the percentages by mass of the individual isotopes of boron 10 and boron 11. So how do you go about this? Well, we have to work backwards. We've got 2 unknowns. We don't really quite have 2 equations, though. Think about what we need. We know that the fractional abundance of boron 10 times 10.0129 AMU plus the fractional abundance of boron 11 times 11.0093 AMU equals 10.81 AMU. So I know that. I'm trying to find this value and this value. So I'm going to label them X and Y. I do, however, know that X plus Y has to equal 1. How do I know that? These are the 2 naturally occurring isotopes of boron, which means that the percent abundance of these 2 species added up together equals 100% of the boron atoms. So I know the fractional abundance, if the percent abundance has to equal 100, the fractional abundance has to equal 1. So I can say Y is equal to 1 minus X and substitute this in to the equation. So I'm going to have X times 10.0129 AMU plus 1 minus X times 11.0093 AMU equals 10.81 AMU. Now I'm not going to write units throughout this whole calculation because they just kind of get in my way, but don't leave your units off at the very end. Or realize at the very end we're going to talk about it, but we'll realize that your units actually do cancel out at the very end. They divide out from each other. So to simplify this means I have 10.0129 X plus, distribute this through, 11.0093 minus 11.0093X equals 10.81. Get your variables on one side and your values on the other. 11.0093 minus 10.81 is equal to 11.0093 x minus 10.0129, 129x. And I forgot to finish calculating this out, so 1 second, I apologize. 11.093 minus 10.81 gives me a value of 0.283. And this equals 11. I put that in my calculator wrong. 0.1993. 11.093 minus 10.0129 gives me 0.9964x. I'm going to move up over here. I'm going to solve for x. So x is going to be equal to 0.1993 divided by 0.9964. That gives me 0.2000, which means the fractional abundance of B10 is 0.20. In percentage form, that's 20%, which means that the fractional abundance of boron 11 must be 80%. So again, I solved for x here, and x was representing the fractional abundance of B10. Y, which represents the fractional abundance of B11, put back into percent, would be 80%. Example 28. If a copper penny from 1980 has 2.94 times 10 to the 22nd copper atoms, what will be its mass? Assume 100% copper. Why does it matter that's from 1980? In 1983, pennies actually changed composition. Pre-1983, pennies were comprised of, I believe it's like 97% copper, bulk copper, but copper became a commodity. Copper's actually kind of expensive compared to other metals. So now pennies are made of about 97% zinc, and they're just coated in copper. So if you've ever done the copper penny experiment, if you scour a penny or scratch it so you can expose the inside and you put it in acid, when you come back, if you put it in acid for a while, come back and look, the penny will be hollowed out and you'll have a copper shell. It's because most people do this with hydrochloric acid or HCl, and the HCl eats away the zinc. It's an electrochemical reaction we'll talk about later, but it eats away the zinc inside and leaves the copper behind. It's kind of a cool experiment, but that's why we specify 1980 here. So copper penny has 2.94 times 10 to the second copper atoms. What is its mass? When I say mass, even though I didn't specify it here, I really mean grams. So I want to know the number of grams of copper. I have 2.94 times 10 to the 22nd copper atoms. I'm going to go ahead and convert to moles. So 1 mole of copper atoms contains 6.022 times 10 to the 23rd copper atoms. This cancels out my number of copper atoms and gives me moles of copper. Now I'm going to use the atomic mass of copper, 63.55 grams of copper for every 1 mole of copper. Calculate this in your calculator and you should get 3.10 grams of copper. So if a copper penny contained 2.94 times 10 to the 22nd copper atoms, it would weigh about 3.1 grams. 3.10 to be more accurate. How many copper atoms are present in a 2017 penny with a mass of 3.10? Modern pennies are 97.5% zinc and 2.5% copper. So I want to know the number of copper atoms. I'm starting with a 3.10 gram sample of the penny. I know that if I have a 100-gram sample, 2.5 grams of that sample will be copper. So I'm going to use that as a conversion factor. 97.5% plus 2.5% equals 100%. If I assume 100 grams, that means that 97.5 grams would be zinc and 2.5 grams would be copper, which means if I had 100 grams of pennies, 2.5 grams of that would be due to copper. Then I'm going to convert from grams of copper to moles of copper. So 1 mole of copper, atomic mass 63.55 grams of copper. And lastly, Avogadro's number, 6.022 times 10 to the 23rd, copper atoms to 1 mole of copper. Make sure everything's canceling out. So again, I've got grams of pennies to grams of pennies, grams of copper to grams of copper, moles of copper to moles of copper, and I'm left with copper atoms. This gives me 7.34 times 10 to the 20 copper atoms. Again, it's really hard to tell, is that number reasonable, because it's just so dang small. But it's actually quite smaller than Avogadro's number. It's a very large number, yes, but Avogadro's number is massive. So it is a reasonable number. And the last example for this chapter, the density of copper is 8.96 grams per mil. How many copper atoms are in a sphere with a volume of 0.475 centimeters cubed? So I want to know the number of copper atoms. I know I have a sphere that has a volume of 0.475 centimeters cubed. I know that 1 milliliter equals 1 centimeter cubed. And I was given density, which makes life a lot easier. I can use that as a conversion factor. 8.96 grams of copper to 1 mil of copper. I don't like remembering the equation for a sphere. Brings back memories of high school, which is fine. Like, I like geometry just fine, but it's been a while, and I don't like remembering all the different equations. So when I see the word sphere, my immediate thought is, do I need to know that equation? But thankfully not this time. I'm now in grams of copper, so I'm going to convert to moles of copper. 1 mole of copper So 1 mole of copper equals 63.55 grams of copper times Avogadro's number. Again, here we've gotten rid of our grams of copper. I'm in moles of copper, so I can use Avogadro's number, 6.022 times 10 to the 23rd copper atoms to 1 mole of copper. And when I calculate that out, I get 4.03 times 10 to the 22nd copper atoms. That is the end of the extra problems for chapter 2. I hope this helped.